Hello everyone, welcome to Chem76A. Today we will begin chapter number 7. In previous chapter we learned the reactions of alkene. In this chapter we will expand that discussion to include the reactions of alkynes. Alkynes are compounds which contain carbon-carbon triple bond as shown in these two molecular structures. If you recall the chemical bonding learned in chapter number 1, you can recall that a triple bond is made up of one sigma bond and two pi bonds. The carbon atoms which make the triple bond, they are sp hybridized, and the sigma bond is a result of head overlap of sp hybrid orbitals, and the pi bonds are a result of side overlap between the two p atomic orbitals. For example, the simplest alkyne is ethyne, and if we compare the uh, orbital structure of alkyne, so we'll see that these are the sp hybridized orbitals of carbon. So this head-head overlap is responsible for the sigma bond, and there are two vacant p orbitals. One is perpendicular, so this side overlap is responsible for one pi bond. The other p orbital is horizontal, so this side overlap is responsible for the second pi bond. So therefore an alkyne is made up of one sigma bond and two pi bonds. Now because alkenes and alkynes are similar in structure, because both of them have some combination of a sigma and a pi bond, therefore both of these kind of molecules undergo similar chemical reactions. Alkynes also undergo electrophilic addition reactions with the Br and halogens and water, which is similar to alkene addition reactions. Alkynes also undergo hydroboration and hydroboration oxidation, and the metal reduction reaction. So most of the reactions of alkynes are similar to alkenes. So therefore this chapter will be a little bit easier to understand because we already know most of those reactions and their mechanisms. So this chapter should be easy. One reaction where alkynes differ from alkene is the reaction with the strong bases, in which the terminal alkynes can be converted into sodium salt of alkynes. So this species act as a strong nucleophile, and this can be used to extend the carbon-carbon chain length. This is one of the rare reactions in which we can increase the chain length. We will study this reaction in detail few slides later. According to Iupsc rules, the infix yn is used to show the presence of a carbon-carbon triple bond. So therefore the smallest alkyne with only two carbons is called ethyne, and an alkyne with three carbon chain will be known as propyne. The Iupsc rules for naming alkynes is similar to the ones for alkanes and alkenes, and it also involves the same four discrete steps. In the first step, we identify the parent chain. It's the longest chain which also include the triple bond. For example, in this example, the longest chain is 4 carbon long chain. And the second step is we number the chain and identify the substituent. And while numbering, we give preference to the triple bond. So therefore, in this first example, numbering starts from the right hand side, because numbering from here, the alkyne triple bond gets the smallest number. So parent chain is 4 carbon long, numbering starts from the right side, and we identify the substituent, which is methyl in this case. And in the third step, we assemble the substituent alphabetically, and then in the final step we write the name together. So in this example, the methyl substituent is at number 3 position. So therefore, and it's only one substituent, so that's written in the front. So the name is 3-methyl, and then we identify the name of the alkyne, but before the name we use the number to identify the location of the triple bond. So 1 butene means that the triple bond is at position number 1. In the second example, the longest parent chain is 7 carbon long, and we give preference to triple bond while numbering it. So therefore, numbering starts from the left hand side, and the triple bond location is at carbon number 3, and carbon number 7 has 2 substituents. Both of them are methyl. So therefore, when we assemble the name, it is 6,6-dimethyl 3-heptine. And if we have multiple triple bonds, then we use a diene or triene to identify the presence of 2 triple bonds or 3 triple bonds. And we also use the numbers to show the position of the triple bond. For example, in this case, the triple bond starts at number 1 carbon as well as number 6 carbon, and the longest parent chain is 7, so it's a heptine. But because there are 2 triple bonds, so therefore the hydrocarbon is named as 1,6-heptadiene. The most common alkyne whose common name is used instead of Iupsc name is ethine. The common name for ethine is acetylene. And we can use the prefixes which are bonded to acetylene as a common name, although these common names are not that frequently used, but in some older books you will find these common names. You don't have to memorize these common names. As long as you know how to write the Iupsc name, you should be okay. As we know that the carbon atom with triple bond has sp hybridization, and in sp hybridization state, the bond angle is 180 degrees. Because of this 180 degree, any alkyne with a cyclic structure will have enormous amount of angle strain, and because of these angle strains, cyclic alkynes are not favorable structures for alkyne molecules. So hence we don't really see or we don't find cycloalkynes with the smaller ring structures. For example, 6-membered cycloalkyne should have a bond angle of 120 degrees, but 120 degrees is extremely small as compared to 180, which would produce a lot of angle strain, making this molecule highly unstable. So cyclohexane is not found or is not formed. The smallest cycloalkyne which exists is cyclonone. Even then it is quite unstable and it polymerizes at room temperature. The structure of cyclonone is shown here, and it's molecular model is shown here. As you can see that it can adjust its structure such a way that the bond angle is not that far away from 180 degree. From the side it almost looks like a straight linear structure, but even then it's not that stable. So although this angle may appear to be close to 180, but in reality in cyclononine angle is about 160 degree. In fact, it's 155 degree, which is quite far away from the optimum value of 180. So therefore cyclononine has a considerable amount of angle strain, making this molecule highly unstable. The physical properties of alkynes are quite similar to those of alkanes and alkynes with similar carbon chain. Smaller alkynes with lower molecular weight are gases at room temperature. Uh, Larger alkynes are liquid at room temperature, and because alkynes contain only hydrogen and carbon, therefore all of these are non-polar and they are soluble in non-polar solvents and insoluble in polar solvents such as water. Their densities are also quite low compared to density of water, so therefore they float on water surface. In chapter number 4, we learned that alkynes have the lowest pKa value among hydrocarbons. The pK value of ethyne and other terminal alkyne is about 25, which makes it stronger acid than ammonia. So ethyne pK value is about 25 and ammonia has pK value of about 38. Therefore, alkynes are stronger acids than ammonia, but they are weaker acids than alcohols and water, because alcohol pK value is approximately about 16. So alcohols are much stronger acids than ethyne. Now terminal alkynes, they react with the sodium amide to form alkyne anions. So for example, if I have any terminal alkyne such as propyne or even ethine, if we treat it with a strong base, the emphasis is on strong base. Although we can say that, oh, sodium hydroxide is strong base, but that sodium hydroxide will not work. I'll explain in a minute. We need a strong base such as sodium amide. So terminal alkynes react with sodium amide to form alkyne anion. In this reaction, sodium ion is just a spectator ion, so it does not play any part. So let's remove the sodium ion from the amide. Only amide, anion from sodium amide participate in this reaction. So this reaction is an acid-base reaction. So where the amide attacks the proton and the product will be sodium acetylide. But in this case again, sodium ion will be a spectator ion. So let's remove the spectator ion, and now in this reaction, propyne is donating a proton, so therefore it is an acid, and amide is accepting a proton, so therefore it's acting as a base. In the reverse reaction, ammonia would be the conjugate acid and acetylide it's a propylide ion. So this would be conjugate base. In the forward direction, the acid is propyne. Its pKa value is about 25, and in the reverse reaction, the acid is ammonia and its pKa value is 38. We know that smaller pK value means stronger acid, so therefore our alkyne is stronger acid and ammonia is weak acid or weaker acid. So therefore we know that whenever an acid-base equilibrium is always favored from stronger to weaker. So therefore in this case the equilibrium will be favored towards forward direction. So hence in this reaction we will get a alkyne anion. So this is our alkyne anion. Alkyne anions are used in many reactions as a strong nucleophile. So alkyl anions are extremely strong and versatile nucleophile, and we will see their reactions in few slides later. Now, although we may say that sodium hydroxide is also a strong base, is it possible to have similar reaction with sodium hydroxide? The answer is no. Let's write the acid-base equation with sodium hydroxide. In case of sodium hydroxide, if we reacted with any alkyne, the base is the hydroxide ion, and then the product will be again the alkyne anion and water. Now pK value of alkyne is 25 and pK value of water is 17. In this case you can see water is much stronger acid, so therefore equilibrium will be shifted towards backward and forward reaction will be extremely small. So therefore this reaction is not possible. We need a base whose pK value is much higher than 25. Only then this reaction will work. So amide is a suitable base. Hydroxide is not. Hydroxide is much weaker base compared to amide. Apart from sodium amide, there are a couple of other strong bases available which can convert terminal alkyne into alkyne anion. So most commonly used bases are sodium hydride and lithium diisopropylamide. These bases are capable of removing the proton from any terminal alkyne and convert that alkyne into alkyne anion. Because as we saw, water is a stronger acid than terminal alkyne, so therefore hydroxide is not a strong enough base to convert alkyne into alkyne anion, so this reaction will not take place. Alkyl anions are both strong bases as well as strong nucleophile. So because they act as a strong nucleophile, they participate in a reaction called nucleophilic substitution reaction with alkyl halides to form new carbon-carbon bonds, and the end product will be a longer alkyne. This kind of reaction is known as alkylation reaction because at the end we connect a alkyl group to our nucleophile. We will learn nucleophilic substitution reactions in detail in chapter number 9. For this chapter, we only gonna take a look at what this reaction is, because this reaction is an important method to prepare longer alkyne starting from a smaller alkyne. So I'm gonna briefly explain what a nucleophilic substitution reaction is. In a nucleophilic substitution reaction, we use a strong nucleophile such as an alkyl anion. For example, in this case, we can use acetylide anion. Of course, there is a sodium counter ion. That's just a spectator ion, so it doesn't really participate in the reaction. So in reaction mechanism, we don't really show the presence of sodium ion. So our nucleophile alkyl anion attacks a alkyl halide. Alkyl halide is a alkane with a halogen attached to it. For example, bromide. The reaction takes place in such a way that our nucleophile attacks the carbon where the halogen is connected, and halogen leaves the alkyl chain. So hence we can say that the nucleophile, this nucleophile is substituting the leaving group, which is halogen. So therefore the reaction is known as nucleophilic substitution reaction, because you'll see at the end our nucleophile will substitute the leaving group. There will be a new carbon-carbon bond formed between the alkyl group as well as our nucleophile. So this is the new bond which forms between the alkyl group and our nucleophile. So as you can see, the end product is a formation of an alkyne, but it is longer. The leaving group, of course, will form a salt with sodium ion, so that also leaves. So nucleophilic substitution reaction is important method to prepare longer alkynes. If you want to prepare even longer than 4 carbon, we can extend the alkyl halide chain and we can design any kind of alkyne to be synthesized. One thing we should remember is that nucleophilic substitution reaction only works if our alkyl halide is primary. For secondary and tertiary halide, another kind of reaction occurs, and that reaction is elimination. We will learn more about elimination reaction again in chapter number 9. So I'll just briefly gonna explain what elimination reaction is. So for example, if we have a secondary alkyl halide, such as this example, so that's a secondary alkyl halide, and we attack it with the same nucleophile or alkyl anion. Instead of replacing the halogen in the way it did in previous reaction, what will happen is that now the alkyl anion will act as an acid, because it's act as a base, because it's also a strong base, and it will remove the proton from the adjacent carbon. So this proton removes and this bond goes here and leaving group leaves, and the end product in this case would be the formation of an alkyne. Nucleophile will just act as a base and grabs a proton, so there's acid base reaction, and plus we will get an alkene in this case, and plus the leaving group. So this kind of reaction is known as elimination reaction. And we will learn the mechanism and more details about elimination reaction in chapter number 9. Alkylation of alkyne anions is the most convenient method for synthesis of terminal alkynes. The alkyne anion can be prepared by reaction of a strong base and an alkyne, such as ethyne. So ethyne in presence of a strong base such as sodium hydride will generate alkyne anion, and then we can use this alkyne anion to synthesize any alkyne of our choice. For example, imagine if I want to prepare a 1-hexyne. All I need to do is I need to choose a suitable chain in the alkyl halide. I already have 1 and 2 carbons here, so in order to go for hexyne I need 4 more carbons, right? So I will use a alkyl halide with 4 carbons, so that would be 1, 2, 3 and 4, and I'll use a leaving group here, so this will attack here, leaving group leaves, and I will get my 1-hexyne. So this way you can make any hexyne as long as it's terminal starting from ethyne. Now you may ask, oh, how do we make a alkyne which is not terminal, where the triple bond is in the middle of an alkyne? That can also be easily done. All we need is, in that case, is not start with an ethyne. So for example, imagine I want to prepare 3-hexyne instead of 1-hexyne, right? So 3-hexyne means that I need a triple bond in the middle. So this would be 3-hexyne. So 1, 2, 3, 4, 5, 6. So that's a 3-hexyne. So how to synthesize this? Method is still the same. All I need to use is, now I need to alter my the alkyl anion. So instead of using the ethyne, I would need to use this alkyl anion, and so this one already has 1, 2, 3 and 4 carbon. I need only 2 more carbons, so therefore I will use this alkyl halide. So method is still the same. So this attacks here, leaving group leaves, and I will end up with 3-hexyne. Now you may ask how to get this one. And remember, alkyl anions are not, although they are stable, but they cannot be stored for long. So most of the time we have to make these alkyl anions immediately whenever we want to use them. So method of synthesis of alkyl anion is pretty easy. So start with the suitable alkyne. For example, to make this alkyne, I will start with alkyne and then add a strong base such as sodium amide or sodium hydride, and this will convert our alkyne into alkyne anion, and then the same alkyl anion can be used here. So now we can see here that alkylation of alkyne anion is one of the most important method which can be used to synthesize various alkynes. Another method to prepare alkynes is the treatment of vicinal dibromoalkanes with 2 moles of a base, most commonly sodium amide. Now, vicinal dibromoalkanes are those alkanes in which a bromo group is present at the adjacent carbon atom. For example, this is an example of vicinal dibromobutane. So as long as 2 bromo groups are present on adjacent carbons, the molecule will be known as a vicinal dibromoalkane. So treatment of vicinal dibromoalkanes with a strong base such as a sodium amide will result in formation of an alkyne, and the triple bond will form between the carbons where the vicinal bromo groups are present. And it will also result in formation of 2 moles of sodium bromide and 2 moles of ammonia. This reaction is carried out in liquid ammonia at negative 33 degrees Celsius temperature. Now in this reaction, the bromo group and the hydrogen groups are removed. So these groups are removed, and instead we get a triple bond between those carbon. So therefore this kind of reaction is also known as dehydrohalogenation reaction, which means removal of hydrogen and halogen from adjacent carbons. Now, so we need vicinal dibromo alkane to prepare a alkyne. However, in order to prepare vicinal dibromoalkane, we can use alkenes. So alkenes are a good source to prepare vicinal dibromoalkanes. So all we need to do is we need to take the suitable alkene. For example, in order to prepare this vicinal compound, we will need to use butene. And the treatment of alkene with bromine in presence of dichloromethane will result in formation of a vicinal We learned this reaction in previous chapter. It's the anti-addition, but this is a vicinal dibromoalkane. So this is same compound as this. So alkene can be used as a starting material. So therefore, in first step, we will need to treat alkene with bromine to get the vicinal dibromoalkane, and then the dibromoalkane is treated with a strong base in presence of liquid ammonia to get alkyne. So 2 moles of sodium amide will be needed, or 2 moles of base will be needed for this reaction, because we are removing 2 HBRs. This equation shows the similar reaction which we saw in previous slide, but in this case our alkene is 1 hexene and our final alkyne is 1 hexene. So this equation shows the synthesis of 1 hexene starting from 1 hexene. So again, we treat our alkene with the halogen to get a vicinal dibromohexane, and then vicinal dibromohexane is treated with the strong base to get finally the hexene. One thing interesting is here that instead of 2 moles of a base, now we need 3 moles of a base. Why it's so? The reason is, after using 2 moles of a base, or when we get the alkyne, so we should get alkyne immediately after using the base. However, because our alkyne in this case is a terminal alkyne, and we know that terminal alkynes also react with strong base to give us the sodium salt of that terminal alkyne. So therefore we need one additional mole of the base. And secondly, in order to convert the sodium salt into our desired alkyne, we need to treat it with water. So that's one additional step. So reaction of vicinal dibromohexane with the base will not yield our alkyne directly, because yes, it will yield the alkyne, but alkyne will react with the base immediately to give us the anion of that alkyne. So to convert that anion into our desired alkyne, so we have to hydrolyze it. So reaction of water will generate our alkyne back. Dehydrohalogenation of vicinal dibromoalkanes is a useful method to prepare alkynes. However, in certain cases, there is a chance of formation of a side product. Let me write an equation in which we start with a dibromoalkane as shown here. And if we treat this alkane to 2 moles of a strong base such as sodium amide, we should expect to see 2-hexyne plus some other products. Although we wrote this equation in one step, but actually this reaction takes place in 2 steps. We're not going to learn the mechanism of this reaction yet, but I'm just going to explain how the steps take place. So in first step, one of the hydrogen and Br are eliminated, and so that would be step number 1. In step number 1, 1 mole of base will be used, and we will get a alkene with Br and hydrogen. So in this step, 1 elimination took place, and then after that a second mole of base will be used, and the second hydrogen and Br will be eliminated, and we will see our alkyne. So this is how this reaction actually takes place. Now in case of dibromo alkanes, where there is at least one adjacent hydrogen near the double bond. For example, in this case we have hydrogens on the adjacent carbon atoms in both sides. We need at least one. In those cases, there is a chance of a side reaction in the second step, and that will take place that instead of eliminating these 2 hydrogens to give our actual product, so what will happen is that this Br and one of the hydrogen from this carbon will get eliminated. So there are 3 hydrogens here, so instead of the usual elimination takes place on the other side, and this will end up giving us a product that's going to be a side product. So in the side product we will see a double bond on both sides of carbon atom. So that's our side product. And remember, this side product only forms when there is a neighboring hydrogen, such as here. There are 3, we only need 1. So elimination of Br from the wrong side of the carbon will form this side product. This kind of side product, or this kind of product, is known as alene. So alene is a compound where a carbon atom has double bonds on both sides. And in alene, there will be 3 adjacent carbon atoms, and all 3 will be sp2 hybridized. Excuse me, the middle carbon atom is not sp2. In fact, the middle one is sp hybridized, but the side carbon atoms are sp2 hybridized. The molecular orbital diagram of the simplest alene, which is 1,2-propadiene, is shown here. As we can see here is that the two pi bonds are perpendicular to each other. So the p orbital from the middle carbon atom overlaps to the side carbon atoms at perpendicular to each other. Most allenes are less stable than their isomeric alkynes. For example, allene itself is less stable by 6.7 kilojoules per mole than its constitutional isomer propyne. And 1,2-butadiene is less stable than 2-butyne by 16.7 kilojoules per mole. Because of their lower stability relative to isomeric alkynes, allenes are generally the minor product of alkyne forming dehydrohalogenation reactions.